This is 3.1.4, the power chain rule, as we continue to talk about the chain rule and how to use it for derivatives. No new vocabulary here, but we do have the power chain rule to learn. So the power chain rule is an extension and generalization of the chain rule. It says that if u is a differentiable function of f, then we can think about the composite function f of g of x as f of u of x and replace that in the chain rule formula. So where we end up with something like this: the derivative with respect to f of the function f of u is equal to f prime of u times du dx. This is derivative of the outside, keep the inside, times derivative of the inside. So that's not really anything new other than a new way to think of it. But thinking of the chain rule that way allows us to generalize the chain rule into a situation where the outside function f looks like a power rule function. It looks like a polynomial of u, the inside function, raised to n, an integer power. So if that's the case, then the derivative of f of u would be n to the front times u, now to the power of n minus 1. So if u is a differentiable function of x, we can use the chain rule to extend this to the power chain rule, so that if we have the derivative of u to the n, where u is a function, that derivative is n u to the n minus 1 power times du dx. Or in other words, if we were asked to differentiate a function such as 2x minus 1 to the third, we could look at an answer of 3 to the front times now 2x minus 1 squared. That's your u inside function squared. There's the power rule part. Now the chain rule part times the derivative of the inside function, which is 2, for a final answer of 6 times 2x minus 1 squared. Here's an example. Let's find the slope of the line tangent to the curve y equals the sine of x to the fifth, where x is pi over 3. So we're looking at this function, y equals sine of x to the fifth power, or sine to the fifth of x, and we're wondering initially, why is that in the category of a power chain rule? Well, it's because of the way we notate trig functions to a power, because we know that y equals sine to the fifth of x is actually another way of saying sine of x all to the power of 5. And so what we look at then is the sine of x is your inner function u, and it's being raised to the fifth power as part of the outer function. So let's do part A. If we want to find the slope of the line tangent, we know we're looking at a derivative. So dy dx is equal to, first we'll differentiate the outside function, which is u to the fifth. So we have 5. Now that's sine of x to the fourth power after we use the power rule and subtract 1 from the exponent. Now we link it up with the chain rule times the derivative of the inside function sine of x, which is cosine of x. And so this is going to be then 5 sine to the fourth of x times cosine of x. We want to know the slope of the line tangent at the point where x is pi over 3. So now we need to plug in x equals pi over 3. So we have 5 times the sine of pi over 3 to the fourth times the cosine of pi over 3. So this is 5 times, well, the sine of pi over 3 is root 3 over 2. And the cosine of pi over 3 is 1/2. So 5 times, this is going to be a 9/16 times 1/2 for a final answer of 5 times 9 is 45 over 16 times 2 is 32. There's the slope of the line tangent to the curve at pi over 3. Now for part B, show that the slope of every line tangent to the curve y equals 1 over 1 minus 2x quantity cubed is positive. So here's that function, y equals 1 over 1 minus 2x quantity cubed. And before we differentiate and think about the slope of a tangent line, it's probably beneficial to us at this point to do a little algebra, because this looks like it might be a quotient rule problem. We have a numerator and a denominator, but with a bit of algebra, we can turn this into just a chain rule problem by taking the base 1 minus 2x, bumping it up to the numerator. So we have 1 minus 2x. Now that power or exponent is no longer positive 3. By moving the base, it's now negative 3. So this function is equal to 1 minus 2x quantity to the negative third power, which means its derivative by the chain rule is negative 3 to the front times 1 minus the quantity 2x. Now, negative 3 minus 1 is negative 4 for the exponent. Now we link it up with the chain rule times the derivative of the inside function. Derivative of 1 minus 2x is negative 2. So now this looks like negative 3 times negative 2, or 6 times 1 minus 2x to the negative fourth. And then if we rewrite with positive exponents, that's a 6 on top, and that's 1 minus 2x to the power of 4 on bottom. So we want to use this expression, the derivative, which is the slope of any tangent line, and use it to show that every slope is positive. Well, here's how I do that. The numerator 6 is positive, and the denominator 1 minus 2x to the fourth power, anything raised to a power that's even is positive, and a positive divided by a positive is positive. Therefore, 6 over 1 minus 2x to the fourth is positive. And that takes us to our last example of this section, and it's really not a problem for us to solve. It's more of a reminder that we want to make sure we keep in mind derivatives of trigonometric functions are assuming that the input is always in radians and never in degrees. The derivative of sine of x is cosine of x only if x is in radians. The derivative of tangent of x is secant squared of x only if x is in radians. And the chain rule allows us to see why that's the case. Because 180 degrees is the same as pi radians, we know that x degrees would then be pi over 180 times x radians, or pi x over 180 radians. So if we substitute that in place and use the chain rule, the derivative with respect to x of sine of x, so this is degrees, would now be the sine of pi x over 180. So that's the substitution. So that's a derivative that's done by the chain rule, and the derivative would be outside cosine, keep the inside pi x over 180, times, here's the chain link, pi over 180, which is the derivative of the inside function. So now we have the derivative of sine x degrees is pi over 180 cosine of x degrees. So there's this extra scalar multiplier out front if we were to allow the input to be degrees. And if we check out the graph of this situation, it becomes even more apparent what's going on. So in Desmos here, the red curve is the sine of x, and the blue curve is the sine of pi x over 180. And we notice that those two do not look anything the same. And we would have to actually change the x-axis so that we're all the way over to maybe like 200, so that we can finally see that the blue graph does indeed look like sine. It is just stretched in the horizontal immensely, so that sine of x undergoes many cycles or waves of its sine before the blue graph even gets done with half of one of its cycles. So just keep in mind that when we take the derivative of trigonometric functions are always in radians. And it's just a good idea in calculus to keep your calculator in radian mode at all times. We don't want to get tricked up with degrees. And that's the end of our study of chain rule.